So depending upon temperature conditions, the solvent that you are taking, so we will be having different kinds of spectra, and we need to identify which particular iron we are talking about. And with that, we are done with the all the lectures that have been required to cover in this particular syllabus of circular dichroism and MOSFET spectroscopy for the chemist. And now we will take up the questions. So whatever we have covered in today's lecture, is there any doubt? So we can take up, otherwise we can start with the assignment problem. Is there any doubt?
No doubt.
Okay. So now you please try this question. First question says, to record the mass bar spectrum of iron containing the samples, a source is used. The source, it is being named as X. X after nuclear transformation to Y gives gamma radiation, which is used in mass bar spectroscopy. You need to identify what is X and what is Y. So we have already read and learned in start of the lecture how the mass bar spectroscopy starts, what is the source that we are using, and after that, what actually we get. So can you please identify? This we have.
Second option, cobalt 57, beta emission.
Did we really have the beta emission? Or it was just the, because when you are going from 57 cobalt to 57 iron, only the atomic number is changing. So is it because of the beta emission? Because that mass will also change in that one. So it really happens with the electron capture. You remember the earlier notes that we have covered? I can show you that. So just check your notes that we have covered in lecture, I think, starting lectures of week 8 or 7. So we wanted to have an excited state of cobalt. So we start with this cobalt thing, iron 57, 27. And that is I is equal to 7/2. So it gives us iron 57 because we want 57, that is only mass per active, but it is 26. So what is this? This is a loss of 1 electron, right? So what it does, it captures 1 electron, and therefore we get 26 over there. So that's why when we are starting with iron, we need to start from the source. As I said, source and sample has to be same, but source needs to be in excited state to release the gamma radiation. And for that matter, we use 57 cobalt. 57 cobalt takes up the electron, and therefore the atomic number goes to 27 to 26. That is of iron, and therefore this becomes our source now. And when it converts to, it goes from 7/2 to 5/2 to 3/2. that releases energy, the emission happens at that gamma radiation. It takes by the sample, and therefore we can have the absorption of the gamma radiation. So it is actually the 57 cobalt and the electron capture. So is this clear? These kind of questions, do not forget the earlier concepts. Keep everything in line with each other. Use the concept properly and then compile everything. So in the final exam, you would be having questions from every section. So you cannot just depend upon the examples or finding out the isomeric shift value or the delta EQ. So you need to know from where we have started, why mass bar spectroscopy we actually started. Now is this clear?
Clear.
Now, this would be a bit tricky thing, but I feel like you can try to analyze it. In mass bar spectrum of a sample containing iron recorded in the presence of a static magnetic field, the number of possible allowed transitions. I don't know whether this has been, I think we have not covered this part, but this is a bit important, so we will discuss it at the last. So firstly, try this. Among the following, those which can be acting as Moss bar nuclei are. So you have four options. Which ones are the possible combination of giving Moss bar spectra? This generally we need to know. This we also have covered in start of the lecture. So one answer is clear, whether cobalt is Moss bar nuclei.
Cobalt is mass bar nuclei, ma'am.
Yeah. So B option.
Iodine 129 also mass bar nuclei.
57 is already there and 121 is also there. So the option is A, C, and D, right? Similarly, many examples, but you need to identify which one are the Moss bar nuclei. Now try this one. This we have already tried in earlier assignments, so that's why I'm just giving you a repetitive example so that the concept would be very, very clear. For the complexes A and B, where iron CN6 4 negative, iron CN6 3 negative, which ones are the true? So solve it and then let me know, then we'll solve it properly.
B option.
D.
Isomeric shift is more positive for A than B.
Okay.
Another one is electric field gradient only exists for B and not A.
Okay, then we'll check it out. So we have iron CN6 4 negative and iron CN6 3 negative. So here it is X minus 6 minus 4. X is equals to plus 2. Here X minus 6. Outside charge is minus 3. X is equals to plus 3. That means iron is existing as plus 2 oxidation state. Now it is D6. It is low spin or high spin. It is low spin because CN is your strong field. Similarly here, iron in plus 3, it would be d5 low spin. Now, firstly, we are saying that electric isomeric shift, we already know more the number of electrons because the spin is same. So now we only be looking at the oxidation state. More the number of d electrons, lesser would be the shielding, more would be the shielding effect, and therefore the delta value would be less negative. That means more positive. So isomeric shift for what are the options? More positive we are talking about. So this is complex A, this is complex B. So isomeric shift for A is more positive compared to B. Because here D electrons are more, it will be giving you more shielding effect. When shielding effect is more, then psi square value would be less. When this is less, therefore less negative or more positive delta value. So you were right that isomeric shift value for A is more than B. The second point that we were having is about the electric field gradient. We will just check it. In electric field gradient, we already know that electric field gradient is dependent on two factors. One is lattice contribution, and another one is valence contribution. So in case of iron in +2, D6 low spin, and iron +3, D5 low spin, their coordination is same because they are surrounded by the CN ligand. That's an octahedral. So when octahedral field is there, we don't consider anything else. Now we will firstly draw their electronic that d orbital. So it is low spin, so everything would be paired E2G and EG. Therefore, no valence contribution. Whereas in case of iron in +3, there would be valence contribution would be there, right? Clear this point?
Clear, ma'am.
So it is having EFG. Is it having any EFG?
No.
Why? Valence contribution is 0. What about the lattice contribution?
Lattice contribution also 0.
Why?
Same type of ligands.
And is there anything else that we see in lattice contribution?
John-Taylor distortion.
So is the John-Taylor distortion is there?
No.
Why?
There is no unsymmetry distributions of electrons in E2G and EG.
Right. So now this concept I feel is clear to your mind. So we have isomeric shift is more for A than B, and isomeric electric field gradient only exists for B and not A. So now try the question number 5, which is on ligand exchange, we have iron aqua 2+ with 6 CN ligands. Find the right trend of quadrupole splitting. Here also we have to see the EFG. So we have 3 basically iron, water, positive, iron, water, CN5, 3 negative, and iron, CN6, 4 negative. This we already saw that in iron 2+, D6 low spin, no electric field gradient is 0. Therefore, this should be the last one, right? Iron in 2+, that is high spin, D6 high spin, that is having both electric field gradient में lattice contribution also, valence contribution also. So this would be the one which is going to be have the maximum quadrupole splitting, and this should be the second in number because here it is having lattice contribution due to different ligands. So this we have already covered. So you also try first on from your side, and this is the right answer. Try and explain if you have any issue in understanding this.
Okay, ma'am. B option correct.
Okay. So then we have, try this one.
Number of C2 axis present in the methane. 4, ma'am.
Okay. How?
It is in a tetrahedral shape.
Hmm.
Same molecule.
Tetrahedral. So whenever the axis we are talking about, rather than saying tetrahedral shapes, you need to find out the point group. So what is the point group of CH4? So since this is the,
D4B.
no, point group we are talking about. So this CH4 is having both shape as tetrahedral, also it is having a point group tetrahedral. Right? And we have covered the tetrahedral symmetry elements. So from there you need to find out how many C2s are there. Okay, firstly, hydrogen, this hydrogen, one out of the plane. This is also out of the plane, but this is above the plane, this is below the plane, these two are in the plane. So we have covered this, how and from where the C2s passes. There are actually 6 edges and C2s pass through the opposite edge center. One C2 pass through opposite edge centers. That means one edge comprising of 2 hydrogens, one edge comprising of other 2 hydrogens, and C2 pass through that. So since when we are having 6 edges, and there would be 6 edge centers, so there would be 3 C2. So this way you need to remember that there are 3 C2 axes. You're understanding?
Ma'am, once again explain, ma'am.
Okay, first you tell me, is there any C4 axis in tetrahedron point group?
Ma'am,
Is there any C4 axis of rotation in tetrahedron point group? C4 means how many angle of rotation? How much angle of rotation?
C4 means
Cn is
90,
360.
ma'am.
See 360
90.
divided by n. So when I'm saying C4, that is 360 divided by 4, that is 90 degrees. So do you feel that after giving the 90 degrees rotation, so this is having the equivalent configuration in tetrahedron?
No, ma'am, no.
So it doesn't. So C4 does not exist. C3 exists,
120 degree.
120 degree. Yeah. C3 exists in this one, tetrahedral.
Yes, ma'am.
How it, from where it passes? Here, see, in V2 we have covered, right? So how tetrahedron looks like and from where you will get the symmetry elements. This I have specifically told you regarding the tetrahedral symmetry as well as the octahedral. So I would recommend go back and see again. So here we were explaining to this particular model that each C3 passes through one carbon and hydrogen bond, and rest of the hydrogens, they move in a triangular fashion. That means 120 degrees rotation may they will change their position, and therefore that would give you the equatorial equivalent configuration. Since we have four vertices, since one C3 is passing through one vertex, we have four vertices, so there would be four C3s. Similarly, when I'm saying that there are six edges are like one edge is between H and D, one edge is between H and C. So one edge will comprises of two vertices. So when I'm passing this C2 from one edge to the other edge centers, it will flip your molecule as 180 degrees and will give you the equivalent orientation. Because of this configuration, we say that we have C2s corresponding to opposite edge centers. So there are six edges, six edge centers. So when we are saying it has to pass through two edge centers, so there would be correspondingly three C2s. So I would recommend go back and tomorrow we have a last live session that will be covering the extra topics regarding the character table and group theory. So I would recommend go back and revise all the concepts. If you have any particular problem in any of the topics, then we can have a revision again. Otherwise, it would be very difficult if we are covering final topics and we are forgetting the earlier one. Okay.
Okay, ma'am.
So this question number, because right now, if group theory you do not remember or point groups you do not remember for at this particular point. So question number 7, that is an homework. You need to find out. So the question basically says, how do you differentiate between the facial and meridional isomers of this one through IR spectroscopy? So firstly, you find out the point groups of this octahedral complex, both the isomers, facial as well as meridional. Find out the point groups and then come up with the answer. How the IR spectroscopy, like how many number of bands could be different for carbonyl groups. And this question also you try. Question number, just try this question number and see if you can attempt it. Otherwise, we will explain the answer tomorrow. Clear?
Okay, ma'am.
So tomorrow it's a live session at 5 to 7. I'm again repeating. Sunday we have kept the session. That would be the final session. After that, there won't be any session. Only the exams would be conducted. So if you have any doubt for that matter, you can ask me tomorrow. So tomorrow I will cover the character table or whatever the extra topics that I feel that would be beneficial for answering most of the questions in the exam. So that will be covered tomorrow. And if there is any doubt in all the week sessions that we have taken so far, that also you guys can come and ask me tomorrow. So, but the timing is 5
Okay,
p.m. Do
ma'am.
not join at 7. It's 5 p.m. Right?
Okay, ma'am. Tomorrow 5 to 7 plus.
Yeah. Okay.
Okay, ma'am. I will join.
So revise all the concepts, read the questions, and also watch the professor's videos, and then come up with whatever the questions you are having in your mind. This is the last chance to for me to help you guys regarding all the queries of yours, and then you will be having a final exam and do well in that.
Okay, ma'am. Okay, ma'am. Before 5 o'clock, I refer all the things. If I have any doubt, I noted the doubt.
Right.
And then I ask to you.
Yeah.
Thank you, ma'am.
So, okay, I'll see you tomorrow. Bye-bye.